Hi friends, welcome to our channel. Let's look at problem 3510 again. So minimum pair removal to sort array 2. So first, this is the follow-up on problem 3507. So in the video for 3507, we solved the problem using brute force. And in a previous video, we solved the problem using sorted dict. Previous video. So now we want to solve this using minHeap. So actually, this two data structure typically can solve same set of problems, but of course they also can solve slightly different problems. So here I'm not going to read through the problem statement. So if you have time, I would suggest that you look at the solution using sorted dict. After checking that video, then following up this video should be rather straightforward, right? So in this video, so we are going to actually do the problem in parallel to the solution using sorted dict. You will actually see these two solutions are in an ultimate sense the same problem, right? So in the previous video, in order to follow up the minimum pair sum, so we are using sorted dictionary. But here we know we can use heap. So this is the previous solution. So here I'm going to delete that. But I'm going to maintain this part. So here LR and RI will also be used, but we introduce some different notations. So here first I'm going to so get the length. This will be the same, right? The length of this A. So here I'm going to use a priority heap. So minHeap. So in Python, for example. So now decrease. So this I will introduce this variable. So this variable is actually in parallel to n inversions in the previous video, right? So we have a low and we have a high. So the previous node and the current node, but this slightly different, right? So range n, but I just write range n, and here also write range n. In other words, the current node index, and then in order to get the previous index, you are going to use low. So low index minus 1. So if the current index is I, so you can get I. So in order to get high, how do you get high? So you will get the current index then plus 1, right? So this will be our notations. So notice that I didn't shift to the left by 1. Here I didn't shift to the left by 1, to the right by 1 as in the previous video. So now first we build the heap. So here basically for I, so here we get the pair. So in say enumerate. So this enumerate, so going to give a index, indexing the tuples. So here I will correspond in enumerate first component. So here we want to use say iterables. So pairwise. So basically nums or a. So this is basically a convenient way to get, say for example, you have an iterable 1, 2, 3. So this pairwise is going to give you this one. So 1, 2, and 2, 3, right? So the length of this pairwise will be 1 shorter than the original length of the list. But here we have this one. So we have enumerate. So what we do is, so heap q, heap push. So we push to this heap the corresponding information, this x plus y, the pair sum, the start index and end index, and then the corresponding numbers, right? So this 4 pieces of information. So the reason we have this piece of information is to track the indices after we do, say for example, combination of numbers, and also we should compare this two numbers and this x and y to monitor the change of this variable, decreases or the number of inversions, right? So the reason we need to do this because the nums, the element, actually can be negative. So, but in this regard, in view of this constraint, the second bullet item, so these two examples are not representative in a general sense. We should have some examples involving negative number. So this will be the heap. So you can print out this heap. Parallel queue. So you can run it. So you see, the smallest number is 4, right? So corresponding to start index 2 and end index 3. So these are the two numbers, 3 and 1. The next smallest one will be 7. 7 scores. So this one is because the heap does not, if you print it, not this is the second smallest, but you do the print or do a pop each time you are going to the root of the heap will correspond to the smallest elements. So this is right. Now let's continue. So we're going to comment this out. So notice that this low and high, actually I just get the original one. So for example, let's print out this low, high. So for example, for index 1, so the low corresponding to itself. Then in order to get low, you should move to one step. So you should get low of 0, 1 minus 0. So here 1 minus 1. So here similarly, in order to get high, you need to add 1, right? So this one, let me still comment this out. And then what we do, so we initialize the answer as in the previous video. And then we're going to do val decrease, right? So this is the same as we have inversions. So once we have this, so we should increment the result by 1 anyway. But because we might change some of the things, so if we have already used that, so we shouldn't do comparison. So now let's get this information first. So we get the value, the start index, end index, and the corresponding values. So heap q, heap pop. So pop from the heap. So we want to make sure, so x and y corresponding to numbers. So you will see this. So basically, if x equals nums I, and y equals nums g. In other words, we haven't used them again. So if nums I is greater than nums g, so this introduces a inversion. So we're going to do this one, increment by 1. So now first, because if this is the case for the corresponding smallest one, for this two ij, we're going to shrink them to be 1. So we don't need to actually shrink and pop as in our brute force solution. But what we want to do is high I. So we reset this to be high g, right? And then low of high g is corresponding to I, right? So this is our way to do the conversion shrinkage, right? And then we are going to check if I is greater than 0, in other words, greater than or equal to 1, then the previous value or the previous index or previous node will be low I minus 1, right? Then we are going to monitor the change of this variable, the number of inversions. So if nums previous is greater than nums I, so in other words, so we have this scenario. So we have previous index and I, and so this will be the case. Then we will see if previous is greater than I, so there is an inversion, and also nums previous is less than or equal to v, right? So if we replace the nums I to be the sum, that is, we replace nums I to be the v, so we are going to have the previous number is less than or equal to v. So in this way, originally we have an inversion, and now because of this we have no inversions. So the decrease will be decremented by 1. So this is the one case. Another case is if nums previous is less than or equal to nums I. But now after you replace, so nums previous is strictly greater than v. So originally we do not have reversions, but after you replace nums I with the sum of nums I and nums j, you have reversions. This is possible because nums j can be very negative, can be a small negative number, right? So in this case, decrease will be incremented by 1, right? So either way, corresponding to we shrink this 3 elements in the previous solution and add this 2. So we are going to do this. So we are going to do heap q, heap push. So parallel here, what we want to push is a pair sum nums. So let's see, I changed this nums to be a. So I want to change this to be a, right? We have lots of nums, so let me just change them. So that's a, that's a, right? So here a, that's also a, right? So let's do it slowly so that we do not make a mistake. So here, yeah, a. So what we want to have is a previous plus a I, right? So not ai because we replace this by v, so we have v. And then the index, start index is b previous. So previous, let's see, previous, and the end index will be I, and then we have a previous, and we have the current value will be v. So this is the one. Another case is if the high, right, the high j plus 1 is still unbound, so then we get the next. So the next will be hij plus 1. So if this is inbound, because of the change of this nums I to be the sum of nums I plus nums j, so the, this pair ending at next will also be affected. So now let's track the change of decrease. So if a and j is less than or equal to a next, so originally we have no inversions. So now if v is greater than a at next, right? So current value will be, because j, the value of j is replaced by v, right? So if v is larger than the next, so we introduced a inversion. So we're going to do decrease is incremented by 1. Another case is aj is originally greater than a next. So there's one inversion, but after we change, so v is less than or equal to a next. So this means we eliminate one inversion. So we're going to do decrease decremented by 1. So either way, so we're going to do this. Let's write heap q, heap push. So a so the current value plus a next. So the start index will be I. So then follow-up index will be next, and the value will be v and a next, right? And then we need to do their inversions. So here what we do is we change ai to be v, right, the sum. And then also we can make aj to be, say, none or something else. That's why here, because of this aj, so we do this check, right? So once we have this, once this is the case, so we should always increment this one by one operation. So afterwards, we just need to return the answer. So this will be a full solution to this problem using heap. Let me first run it. So here, let me check that. So here we have, let me see, we have this n parallel hill, decrease, and low, high. Let's see, we have this one. This is also, yeah, here I guess I forgot to compute the original number of inversions. So if x is greater than 1, so decrease will be increment by 1. So now let's check. List, let's see, list out of, so we get this. We get I plus 1, xy. So we have this one. We have vig, xy, ai, and ag. So here, if ai is greater than ag, so we're going to decrement. So here we are going to ai is greater than ag. So we are going to eliminate this one. So we're going to decrement by 1. So let's see. Yeah. So with that, let's submit for the general case. Yeah, it passes all the cases. So in order to better understand the logic, let me do some print operations. So here we can see the original low and high, the original parallel hill, and then here, so we can do some print. So here, let me also introduce a round, right? Round is 1. So round, say round. So now we have see v, I, and j, and x, and y, right? So here you see if ai is greater than aj, because we are going to shrink this, so and we should decrement this by 1. So now we can also print out the before say shrink ij, right? So we see what's the a and also low and high, right? Then we can see afterwards. So let's print that. So basically, originally you have low like this and high like this. This is the priority heap. So after you pop this one, you get v is 4, this I, this g, right? And then before you shrink, you have 5, 2, 3, 1. Then afterwards, so what do you get? So afterwards, you are going to get, because we shrink this 2, we replace them as the sum, so we get 5, 2, 4. And also, if you look at the high, so here this change to be 3, right? And then the next time you are going to have see this v equals 1, I equals 1 and 2, v is 6. So this is the state as here, right? As here. Then after you replace, you are going to replace this 2 and 4 into 6, and then I set this 4 to be none. So that's also, if you see this none, that's actually why we have this check, right? So and then afterwards, the final state of A is like this, and for the first one also is corresponding to the end of this index, right? It's 3, it's because 3 adding 1 is corresponding to 4. This is exactly corresponding to our previous video, the capital R, right? This corresponding to the capital L. So with that said, I guess that's about it for this this solution. So as I mentioned in the previous video, this is a hard problem. So if you are first time, you have some confusion, that's normal. So in order to genuinely digest the details, you need to have a paper and write down the procedure by yourself, and then you will get the main logic. So with that said, I guess that's it for the current video. Thank you for watching.